All right, let's go ahead and get started. A couple of quick administrative announcements. In case you've lost track of the schedule or you haven't seen the course webpage recently, just a reminder that we do not have class on Thursday because we have a midterm Thursday night. See if I can pull up the webpage here. Okay, so the exam will be in 1404 Siebel. Everybody goes to the same room. Don't have this problem with splitting up by letters. The coverage of the exam is going to be essentially everything since we said, okay, this is the end of the midterm 1 material. So specifically, various flavors of recursive algorithms, divide and conquer, backtracking, dynamic programming, greedy, and various flavors of graph algorithms, whatever breadth, depth first search, topological sorting, minimum spanning tree, shortest paths. Now, we will not be emphasizing any of the earlier material, but earlier material may show up because life is cumulative. So in particular, for example, if we happen to give you a DFA, chances are pretty good that we're trying to get you to think about it as a graph, or that we're trying to do some, subsequency dynamic programming thing like we've done on the homeworks. But in that case, the point of the question is not going to be to prove things about regular languages or DFAs, but just as a convenient way to say, here's a graph. Similarly, there may be induction proofs involved. For example, if you're trying to prove that a greedy algorithm works, but those are not going to be the main point of the exam. Okay. There's a bunch of study practice problems. These are all mined from exams from previous semesters of 473, from the labs this semester and last semester, from the exams in 374 last semester. Most of these questions have been asked on exams before, but again, deliberately because studying for this helps you actually learn this. We deliberately put some questions on there that are, we believe, too difficult to reasonably ask you to do under exam conditions. The theory being that if you can stretch towards these harder problems, they'll help you with the easier ones. The exam itself may or may not draw questions from this list, but this will at least give you a flavor of what we will ask. And if you want to calibrate difficulty, what I would suggest is looking at previous exams for 473 and 374, and that'll give you an idea of the kinds of questions we might ask. Please do discuss these questions on Piazza. Please ask questions about them in office hours. Please ask about them in the labs, which are canceled tomorrow. If you happen to be in the room when the TAs are there, please ask them about them here Thursday morning if you happen to be in this room at the same time as I am while the lecture isn't going on. There is a conflict exam, as usual. We're not going to delay over the weekend the way we did last time, because that caused a couple of problems. So by default, the conflict is going to be on Friday, hopefully in the morning. But there may be some people who, for whatever reason, are going to be out of town on Friday. For those people, there's an option to take the conflict exam Thursday morning, which does mean taking the conflict exam before or even during the actual review session. If there's a typical registration survey, it's just a web form that you fill out saying which times you definitely can and maybe can be available. And as it says on the form, if you're thinking, do I take the conflict exam or do I go to the lab, you're available for the conflict exam. Don't claim to be unavailable for the conflict exam because of something else in this class. And because of the possibility of offering the conflict exam for some people on Thursday morning, we really need anyone who needs to sign up for a conflict to register by the end of the day tomorrow, just so that we know how many people are going to be showing up when. Okay. Are there any administrative questions about the midterm? Yeah.
You said that lab is canceled.
Yeah, there's no lecture on Thursday. There's no section on Wednesday, just like for the previous midterm. But the TAs will be in the room as usual on Wednesday, and I will be here as usual on Thursday. Right? The university requires that we officially cancel. If we have evening exams, we officially cancel as many contact hours as we have on the exam. So I am hereby canceling class on Thursday. But of course, I'll still be here because it's already written into my schedule, right? So if you want to come and ask questions, great. Yes? Oh yes, I'm sorry. I should add this to the announcement on the webpage. Same rules as last time. You're allowed to bring in one sheet of paper with whatever you want on it. Generally, what I would recommend is trying to encode some general principles. Much more, I think, will be much more useful than trying to describe particular algorithms. But you may want, a couple of illustrative dynamic programming algorithms to get the feel for what a dynamic programming algorithm looks like. But important things to put on this cheat sheet would be, what do we want you to write down when you do a dynamic programming algorithm? An English description of the function you're evaluating, a recurrence for the function, a memoization data structure, an evaluation order, and a running time. Right? And there'll be points attached to each of those. Yeah?
The rubric for the dynamic program as well.
Exactly like the homework. Exactly like the homework. Any other administrative questions? I want to hold off on actual, content questions until tomorrow and Thursday because we still have some extra, we still have some material to get through in the lecture. Okay. So, on Thursday last week, we started talking about Turing machines as a sort of elementary model of computation. And the basic idea behind the Turing machine is that you have memory in the form of a tape, and then attached to that tape at a particular position, you have a machine that can be in a finite number of states. And the machine can read the symbol at its current location on the tape, and then based on that symbol and its current internal state, it can change its internal state, it can write a new symbol onto the tape, and it can move optionally one step to the left or one step to the right. Okay. Now, actually programming these things is probably best described as tedious, but what I hope from the lab on Friday convinced you is that it's possible, right? That's really the intuition that I want to get across, is that there are simple things that with given enough time and enough attention to detail, you can do with Turing machines. You can copy a string from one position on a tape to a second position on a tape. You can double the length of a string, or given two strings of ones of length A and B, you could, with enough effort, replace it with a string of ones of length A times B, for example. More or less just by using brute force, but just being very, very careful. In this case, this is sort of the assembly language version of, formal. This is a formal version of assembly language, except that you don't even have random access memory. What I mostly want to do today is talk about extensions and variations of this model to convince you that in terms of the things that the model can do, this is in fact no less powerful than models that you might normally think of using, like the virtual machine that you're imagining in your head when you write code in C. There's a machine model that you're programming to that allows you to do things like, access given an address, you can access the data stored at that address in constant time. Those things, even though you may not be able to do them as quickly, you can still do on a Turing machine. So I'm not going to build this up in full generality, so I'm not going to describe, for example, how one implements malloc on a Turing machine. But at least I want to convince you that you can simulate something that resembles a random access machine, that allows you to do, arithmetic operations, and you have a memory that's a big array, and you can say, go get me the thing at address I, and it will return that and put it into some registers and stuff like that. And then the second thing that I want to build up to is the idea that a Turing machine can simulate itself. And really what I mean here is, and again, I'm not going to do this in full, complete technical detail, but the intuition is I'm going to show you how to write a Turing machine interpreter in Turing machine. Right? The nice thing about this model is that it's simple enough that hopefully I can convince you, again, without giving you the complete technical details, hopefully I can convince you that it's mostly a matter of tedious mechanical filling in the blanks to actually make this work. The idea being that the model that we're simulating is simple enough that if we were to write, say, a Turing machine interpreter in Java or Python or Haskell, it would actually be fairly short. It'd be a for loop with a lookup table in it, and under some conditions we break out and return either 0 or 1. Right? That's basically it. So when I say simulate itself, what I really mean is I'm going to describe, or at least sketch, how to build a so-called universal Turing machine. That is, I'm going to show you a single Turing machine that in principle can do everything that any Turing machine can do. And therefore, by something we like to call the Church-Turing Thesis, I'm going to show you, again, sketched, a single Turing machine that can compute anything that can be computed. Okay? So the Church-Turing Thesis basically says any physically reasonable, you say physically realizable model of computation is equivalent to Turing machines. So the Church-Turing Thesis says, for example, Lisp doesn't have any additional power that Turing machines don't have. You can simulate a Lisp machine using a Turing machine, and you can simulate a Turing machine in Lisp. The Python machine, the virtual machine that you program when you're writing Python code, that has exactly the same computational power as a Turing machine. If it is computable on a Turing machine, it's computable in Python and vice versa. Right? So when I say I'm building a universal Turing machine, this means I'm building a single machine that can compute any computable function, which sounds really, grandiose until you realize that this is exactly what a Python interpreter does. A Python interpreter is a single program that can execute any Python program and therefore can compute anything that can be computed in Python with just one piece of code, treating the other Python thing as data now as opposed to a separate machine. Okay? So this is this Church-Turing thesis is functionally taken to be a physical law. It's not a mathematical theorem in any sense because there's no proper mathematical definition of what it means to be either a model of computation or to be physically realizable. But the physicists would say, this is a working rule of thumb that is consistent with all the evidence that we have. As far as computer scientists are concerned, this is taken essentially as a definition for a reasonable model of computation. A model of computation is reasonable if it's equivalent to a Turing machine. Right? There are models of computation that are not equivalent to Turing machines, which are sometimes useful, and maybe you'll hear about them next semester if you take 473. But physicists would say, that's not useful, you can't do that in real life. Okay, why do I care about real life? This is a theory class. And it's a really strange thing to hear from a physicist, too. Right? Why do physicists don't care about real life either? They care about their mathematical models of real life. Anyway, so let's try to build up to things that we can do on a RAM, but do them on a Turing machine. Okay, so one simple thing that the standard Turing machine model has a single head looking at a single spot on a tape that is infinite in one direction. Okay, and each cell on the tape can store exactly one symbol. So the first thing I want to convince you that we can do is that we can pretend that the Turing machine allows a tape with multiple tracks. Okay, so instead of the tape carrying one symbol in each spot, we could instead allow the tape to carry 3 symbols in every cell of the tape. So now, instead of the tape being, think of it as an infinite array where every entry in the array is a single symbol, now I want to be able to think of this as an infinite array where every cell in the array contains 3 symbols, the first one, a second one, and a third one. Now this is actually immediate, right? And the reason is, if I imagine that these 3 tapes each draw symbols from 3 different alphabets, have gamma 1 for track 1, have gamma 2 for track 2, and have gamma 3 for track 3. So for example, maybe track 1 is going to contain zeros and ones, and maybe track 2 will contain A's and B's, and track 3 will contain X's and Y's. And each one of these 3 tape alphabets has its own blank symbol. Then a machine that has multiple tracks, the transition function, instead of taking a state and a single symbol, it would take a state and a symbol from tape 1, and a symbol from track 2, and a symbol from track 3, and it would return a new state, and a new symbol to write into track 1, and a new symbol to write into track 2, and a new symbol to write into track 3, and something to do. Okay? Now, I claim this is actually not more powerful than a standard Turing machine that has only one tape alphabet. And moreover, I claim that I can prove this to you by making exactly 4 marks on the paper. Anyone want to tell me what those 4 marks are? One, 2, 3, 4. This product, gamma 1 cross gamma 2 cross gamma 3, is a finite set. And therefore, it's, by the original definition of a Turing machine, a perfectly reasonable tape alphabet. The end. Right? It's a finite set that we imagine has this additional structure where every element of the set is a triple of symbols, one from here, one from there, and one from the other. But that really doesn't matter. The original definition of Turing machine just says the tape alphabet is some finite set. And so in particular, we can build up finite sets by taking triples of things from other finite sets and gluing them together. Right? So a Turing machine with multiple tracks, each with its own alphabet, is the same as a Turing machine that just has a tape alphabet with some product structure that is convenient, but it's just convenient. It's not an extension at all of the model. But for the sake of intuition, it's often useful to imagine that we can divide the tape up into these independent tracks, in particular because this allows us to do things like the following. So I'm not going to, show you the actual states, but I want you to imagine now. Suppose I wanted to copy this input string 0100101. And I wanted to make a second copy of that string somewhere else. So one thing I could do is I could mark on the second track the character that I'm currently in the business of copying. And I could also mark, just for convenience, the last character, just mark the current character and the last character in the string. And I can do this because I start at the left end in my current state. I read whatever I read, and I put down an X. And then I scan to the right until I see a blank, and then I back up, and I put a blop down on the tape in the second track. Then I go back to the X. I read the character under the X, and as I walk by this blank, I write down a new X. And then I go over to the blop, and then the next blank after the blop. That's the technical name for this, by the way. It's a blop. And I write down the character that I just remembered reading back over the X. And then I scan backwards until I see an X, read this character under the X, and store it in my internal state. Then, as I'm passing by, write down another X. When I get to a blank blank on the tape, I write down that other character. And I scan back, read this, put down another 0, and then eventually I'm going to get to the point where I'm trying to copy the character that has, both of these marks. In fact, maybe I would have been better off putting that end of string mark as a symbol on a third track. But as soon as I copy the symbol that's marked down here on the third track as being the end of the string, then I can stop copying symbols. If I didn't have this additional mark down here, I would just repeat the same string over and over again forever and would never halt. And then once I've copied the string, I could, replace all these additional marks with blanks, and I've recovered a string in the original alphabet, but just doubled. Okay. Now the Turing machine that you developed, hopefully in the lab on Friday, that does exactly this task, basically did this, but by using a different symbol for 0 blank and 0x. Maybe you called these A's and B's instead of zeros and ones with X's under them. The nice thing about having these additional tracks is that you can implicitly, intuitively maintain the symbols while storing information in parallel rather than overwriting things. Okay? Yeah?
So will you essentially double the time?
So time here has a funny definition. Time is the number of times you evaluate the transition function. That is the definition. So if the transition function, by definition, reads in symbols from all 3 tracks and writes out symbols to all 3 tracks, that is one operation of the machine. Right? Now, as you might guess, if you think about this for a while, one of the implications of this is that given any Turing machine that solves some problem in t of n time, I can build another Turing machine that solves the same problem in half the number of steps. And all I do is I build a Turing machine that looks at a window of size 2 on the tape. So now I have essentially, instead of vertical pairs, I have horizontal pairs. Based on my current state and whether I'm on the left side or the right side of this pair, I can figure out in one operation, when I leave this window of size 2, what should I leave behind, and should I leave to the left and leave to the right? And that'll all be one operation, even though in the original Turing machine it would be, at least 2 operations.
So the Turing machine could have multiple reheads?
Oh, yes, we'll get to that. But one of the things to keep in mind about Turing machines is there really is the running time of an algorithm on a Turing machine. That constant factor really depends on the precise details of the Turing machine model that you're using. And just by changing the machine model slightly, you can speed up or slow down the machine by a constant factor. Right? This is one of the justifications for using big O notation, is that it's not only that the constant factors don't matter for what we care about, but they're really, strictly speaking, not even well defined. Okay. All right. So there was a suggestion, maybe we should think about having multiple heads on the tape, multiple places where we can read and write to the tape. So for the sake of argument, let's suppose, all right, that's here. Suppose I want to simulate a Turing machine that has 3 heads. Sorry, we didn't get to do this on Halloween. I've got a Turing machine that has 3 heads. And again, I want to be able to take, define some sort of transition function that takes my current state, just one state, and 3 different symbols from the tape alphabet, and then it will produce a new state, 3 new symbols to write on the tape alphabet, and then 3 actions to take. Each of the heads I can move independently left or right, or keep them still. Okay? So I'd like to have a machine that has essentially 3 different points of access onto the tape. And in a single step, I can read all 3 symbols, and then based on those 3 symbols in my internal state, I'll change my state, I'll write down 3 new symbols, and then I'll independently say move this one to the left, this one to the right, and leave this one alone. Okay? Now, in this case, based on my earlier Turing machine model, which only had one head, there's not really any way to do this in only a constant number of steps. But remember, our goal is not to make things work fast. Our goal is to show if you can compute something using a Turing machine with 3 heads, then you can compute that same thing using a Turing machine with only 1 head. Okay? So here's how I'm going to simulate a 3-head Turing machine using a 1-head Turing machine. Okay, so I'm going to have a tape. But that tape is going to have 4 tracks. Okay, this track is where I'll actually store the data, and these are the tracks that record head positions. Okay, so head 1, I'm going to mark on track 2 with the symbol 1. Head, well, maybe, or just a little up arrow. Head 2, another up arrow, and then head 3, another up arrow. Okay. Now, the actual data, the zeros and ones that might have been on the original tape, I'm going to put here. Okay. Now, my actual Turing machine has only 1 head. And that head is actually going to, by default, start here, over on the left side. And so I'm going to add an extra symbols on the left end of the tape. I'm going to mark the left end of the tape in a way that allows me to know that I'm at the left end of the tape. Okay? So after every transition of the machine that I'm simulating, the machine that's running the simulation is going to return the head to position 0 at the left end. Okay, now what is the machine going to do? I'm going to scan track, let's call this track 1, until I reach the mark that says this is the position of head 1. And then I'm going to look here in track 0, and I'm going to read this character and remember it in my internal state. And then I'm going to return the head back to the end. Then I'm going to scan on track 2 until I see the mark that represents the position of head 2. I'm going to look up in the corresponding place in track 0, read that symbol into my internal state, and then scan back to the beginning of the tape. Then I'm going to do the same for track 3. I'll scan along track 3 until I see the mark that indicates where head 3 is. I reach up to read the symbol that's on track 0 in that location, and then I'll scan back. And at this point, my internal state is a quadruple. My internal state at this point is storing the state that the simulated machine is in and the 3 symbols that the 3 heads of the simulated machine can read. So 1, 0, 1. So now based on this transition, I have this table hard-coded into my machine. Now this is going to return some sequence of things that says I should change to state Q prime, I should change the symbols on the tape to 0, 1, and 1, and I should move all 3 heads to the left. So I'm just going to do these things one at a time. Again, I scan to the right until I see a mark on track 1, and then I write this symbol into track 0 in this corresponding location, and then scan back. Scan forward until I see a mark on track 2, write the corresponding symbol into track 0, scan back. Scan over to on track 3 until I see a mark, write the corresponding symbol, which in this case was already there, scan back. Scan for the mark on the position of head 1, and now move that symbol over based on the direction that's in the transition table. Same for head 2, same for head 3. And then return to the left side, remembering now that the simulated machine is in state Q prime. Now, that took a long time, right? And I wasn't particularly efficient about it. I said, I start here, and I go scan, scan, scan to read, and then scan, scan, scan to write, and then scan, scan, scan to move the marks on the tracks. So altogether, I'm making 9 scans over potentially the entire tape. But this is all done in a small collection of states, which I can essentially treat as a subroutine. Once I have subroutines, intuitively, for purposes of designing algorithms in particular, you can think of that subroutine as an atomic operation. One step. And in fact, it is simulating one step in the multiple head machine. Now, once I have this kind of simulation, at this point, for reasoning about what I can compute, I may as well assume that my Turing machine has multiple heads. I should allow myself to design Turing machines that have multiple heads, and then I can reduce them back to the original model by applying this mechanical back and forth scanning stuff. Okay. It should also be clear here there's nothing special about the number 3. I could, just using exactly the same technique, I could design a Turing machine that has 2 heads, or a Turing machine that has 42 heads. As long as there's some constant hard-coded into the machine for how many heads there are. Okay? So, questions about how this works. This often throws people for a loop because I'm taking one operation and I'm turning it into a lot of steps. And so this totally screws with the running time of whatever algorithm you're playing with. But I don't care right now about running time. Yeah?
So what about this night time?
Yeah, I mean, you could do the reading scans, and then as soon as you've read the third symbol, you could immediately know what you have to write there and write it down and move the token, and then go back and do 2 more scans for the other 2 heads. Yeah, you could cut it down to 5. But 5, 9, whatever. They're they're constants, right? 2, I don't care about time, right? Much rather be systematic and make sure it's correct. Okay. So now, once you have multiple heads, the next step is to have multiple independent tapes. Right? So maybe I have 3 totally independent tapes, each of which has, let's keep it simple for now, 1 head on it that can read or write to a single position on that tape. And then in a single step, I want to read all 3 of these symbols, and then based on my internal state, write out 3 new symbols, and then move each of these heads left or right as I see fit. So how would I simulate a machine like this that has multiple tapes? Using a machine that has only 1 tape. I'm thinking something a bit more direct. I don't want to do any math.
Are those separate?
Yes. Every tape has its own head.
So you could do like kind of what you did in the last example, but then have
So what would so I want to simulate this using a Turing machine that has one tape. What will I have on that tape? Yes. Yes, that's it. So in the simulated machine, I'm just going to simulate three tapes, each with one track, using one tape that has three tracks. And now I'm going to have, one head that can only see track 3, and one head that can only see track 1, and one head that can only see track 2. And now I've gone from having multiple tapes, each with its own head, to a single tape with multiple heads, which then I can simulate, again, using even more tracks, with a single tape with a single head. And then these, multiple tracks, I'm actually doing, immediately by sort of folding them all into just a larger tape alphabet. Okay? So this means that when I'm trying to design a Turing machine to actually solve some problem, I can actually imagine the Turing machine having multiple tapes, each with multiple heads, each reading multiple tracks. All right, so I could have 3 tapes where the first tape has 2 tracks, and the third tape has 3 tracks, and the second tape has 4 independent heads, and the other 2, you mix all these things up. Again, as long as you only have, the number of tapes, the number of tracks, the number of heads, these are all hard-coded constants. Okay? All right, so for this reason, it's often convenient to modify the Turing machine model to actually allow for 3 different tapes as the standard model that we use to implement things. There's an input tape, which is read-only, and it's actually finite, right? So maybe there's a special mark on the beginning and end of this that says you don't read past this. But there's just a chunk of memory that stores the input string, and the actual finite control has access to only one spot in that input tape at any given time, and it can move it left and right, but it can't write new symbols onto the tape. Okay? Then I have a work tape, which I can do any reading or writing I want. Right? And again, my finite controller has access to exactly one location on the work tape. And then possibly, if you're writing, imagining a Turing machine that computes a function, given a string, I want to muck it about and return another string as my output. I could imagine a write-only output string, a write-only output tape, where again, I might imagine that the Turing machine has access to only one spot in the output, but essentially it acts like print a character. The Turing machine can only modify the output tape by writing down a symbol and then moving to the right. Okay? So this allows me to assume without loss of generality that whenever I run the Turing machine, the input is not going to be destroyed, because I may want to call several different Turing machines using the same input string. That the output is not going to clobber the input. I don't have to worry about cleaning up the work tape when I'm done. Right? I just have to remember when I finally compute the output to copy it from wherever it is on the work tape into this output tape. Okay? So again, when we're designing Turing machines to actually compute things, we can give ourselves some additional structure in the machine model without changing our ability, what functions we can compute or what languages we can accept. Okay. All right. So let me see if you can figure this one out for yourself. There's another bit of convenient simplification or extension, depending on how you look at it. Okay, so the standard definition of a Turing machine says that the tape is essentially a string that's infinite in one direction. And a finite number of characters on that tape are not blanks. So there's an infinite sequence of blanks going off into wherever. But I could also imagine allowing the tape to be infinite in both directions. So there'll be some chunk of the tape that actually has symbols on it, and there may be, here's position 0. This is the position where I would start. But there's no left end of the tape to fall off. If I moved left from position 0, I just end up in position -1, and there's a cell there waiting for me to read or write it into. Okay, so can you describe to me how you might simulate a machine that has a doubly infinite tape using a machine that has only a tape that's infinite in one direction but bounded in the other? Yeah. Okay, so here's one way to do this. Is when we hit the left end, shift everything over. Okay, so if, again, I'll have a special symbol that tells me that I'm at the beginning of the tape. But if I find myself here, for any reason, I'll jump to a special state, a subroutine, that shifts everything over, leaving a blank here, and then I'll move the read-write head onto that blank. Right? We've already seen how to shift the entire contents of the tape one step to the right. That was that two-state Turing machine that I showed you on Thursday. So we just do that. We shift everything, then we run back to the beginning of the tape, then we step one step to the right, and there's a blank waiting for us. And now the rest of the Turing machine can behave exactly as if I didn't see this end of the tape symbol, but rather I just saw the blank. So in effect, I put a post-hypnotic suggestion onto the Turing machine. I say, if you ever see this big black square, go to sleep. Meanwhile, some other part of your subconscious will clean up the tape. And when you wake up, you'll actually be looking at a blank. And that black square will just be a horrible dream. Okay? Which means you can design the machine as though it really did run into a blank, as though it really were running on the doubly infinite tape. Just whenever you hit the boundary, you just give yourself some room. That's not the only way to do it. Can anyone suggest a different way? Yeah?
You could say whenever you're writing, what would be the right of the black square?
Okay, good. So you can fold the tape. Okay, so what the tape would actually look like then, and now I'm going to write not the content of the tape, but the indices up here, right? So this is, for example, index 0, 1, 2, -1, -2, -3. right? The indices might look like this. Okay? And now when the machine is here at position 3 and it reads a character, say, okay, I read a 0, that means I should write a 0, I should change to state 17, and I should move 1 step to the left. I go into a post-hypnotic fugue where I go into a temporary state that just says, oh, just move to the left again. Okay? Now, I have to be a little bit careful because when I'm in state 1, when I'm at index 1 and I want to move to the left, I go into my fugue and I move 2 steps to the left, and then I end up on a black square. So I go, at this point I need the inception button. I go into the second fugue state where I say, oops, I flipped over to the other side of the tape. Now left is right and right is left, and by the way, you have to take 1 more step. Now if I'm at index 0 and the instructions in the Turing machine say move 1 step to the left, I actually go, because I flipped that sign bit in my head, I actually now move 2 steps to the right to simulate going 1 step to the left. Okay? So I have to have a bit as part of my internal state basically saying, does Spock have a beard or not? Am I in my own regular universe or am I in the mirror universe? Nobody got that joke. I must be old. Okay, good. I'm not that old. And then, just keeping in mind that when I hit this black box, that's my indicator that I need to flip that bit. And then I always take 2 steps instead of 1, and I do that by having a temporary state that I go through attached to every transition. So altogether, I end up using maybe 4 times as many states as I did in the original doubly infinite Turing machine. Good, that's the second way to do it. There's a third. On another, oh yeah, right, good. So now it's kind of like folding the tape again, except I'm going to use 2 tracks. One to store all the, say, all the non-negative indices, and one to store the negative ones. And again, with a mark indicating the boundary when I should change my sign. Now I don't actually have to add in these additional states that allow me to take 2 steps to the left instead of 1. I just take 1 step. But I still need this extra bit attached to every state that tells me whether I'm in the regular positive universe or whether I'm in the mirror universe, reading the other track in the opposite direction. Okay? Good. All right. So now there are 2 more things that I want to show you how to do. We've done this a little bit already, but not recursively. Okay? So I want to be able to design a Turing machine that in some sense can call itself recursively. Now, what does that mean, right? So that means that in addition to being able to write onto the tape and move the tape head back and forth, optionally I want to allow, 2 additional behaviors. One is push a state onto some stack somewhere This is modeling calling a function. And if you remember from, maybe the computer engineers will remember this better than the computer scientists, when you call a function on one of these, say you're writing a program in C, what actually happens to memory? Yeah? You save the stack frame, right? And that means essentially you take a chunk of memory and you push it onto a stack. But one of the things that you push onto that stack is an instruction counter, that a return address. When your subroutine is done, go here. That's what this push represents. Okay? So I want to imagine being able to say, push this state onto some stack. Save this state. And then I also want to be able to pop. And what pop does is it pops whatever the top state is off the stack and then makes it your current state. Okay? So this is call some function, and this is return from that call. Now, I can push this further. As it stands, I'm not allowing my subroutines to have any arguments. But I could push this further by saying, I could imagine that I have a tape that I write things on. I write a string onto it, and then to call the function, I push the state on, and now that tape is suddenly going to be interpreted as the input tape. And then whatever output tape I write is going to be available to the caller when I return, as a separate output tape. Okay? But for now, let me just imagine that I want to do simple things, that I have global memory, and I'm just going to push states on and off the stack. Okay? How would I actually simulate this using a regular old Turing machine that does this purely iterative? Yeah. I implement the stack with a new tape. Right, so I have my regular, tape that stores data, 0, 1, 0, 0, 1, 0. And then down here, separately, I have my stack tape that, if I'm implementing a stack, basically when I push, I'm going to write a new symbol onto the stack and move the stack head to the right. When I pop, I'll move the stack head to the right and read the symbol that's there and write a blank on top of it. Okay. But of course, this is just a particular way of using multiple tapes, which is, of course, just a particular way of using multiple heads, which is, of course, just a particular way of using multiple tracks, which is just a complicated, vocabulary of tape alphabet. Okay, so hopefully this at least convinces you that I could do more interesting things, like I could pass in, for example, that I could write a Turing machine that computes Fibonacci numbers by doing it recursively. Right? So it's easy to add another 1 onto a string of 1s. It's easy to take 2 strings of 1s and add them together into a longer string of 1s. But by actually writing the recursive Turing machine, I could have something that reads in a string of n 1s and writes out on the output tape a string of the nth Fibonacci number 1s. Right? Literally by just invoking the recurrence, not by turning it into an iterative algorithm first. Right? So I can do things, that involve a small amount of memory, because I, at the moment, still can only access memory locally. but that might be defined recursively in terms of that small amount of information. Okay? So this also means that I can literally take existing Turing machines and call them as subroutines. So when I want to invoke a subroutine, when I hit this call action, what that means is jump to the start state of that other Turing machine. And then I interpret halting for that other Turing machine as a return. Right? So I can literally think of designing Turing machines completely independently, as though they were the only thing in the universe, and then with a simple modification, treat them as subroutines that I can call from other Turing machines. Which is exactly the sort of thing that we like to be able to do on real computers. We like to be able to write simple functions and have more complicated functions call them, or even better, we like to have somebody else write complicated functions and we write simple functions that call them. Right? Let somebody else implement sort. We'll just have some 5-line program that has sort as its first line. You can do that on a Turing machine, right? Which is good. That's something we want for real computers. And then the last thing that I need to be able to convince you of is that I can implement a random access memory. Now, question. Yeah. So basically, I have to say, okay, I have this Turing machine over here, and I'll tell you that this is the start state and this is the halt state. And so when you're designing your Turing machine to call mine, at some point you push a state onto your call stack and then jump to my start state. And when this machine enters its halt state, that's the signal for you to pop the state off the stack. Right, in fact, it's fairly natural to implement halting as you tried to pop something off the stack, but the stack was empty, which is exactly how halting works when you actually write C code. Right. Okay, so random access memory. Turing machines, by definition, can only access the memory that's directly under the current head or heads. In fact, what I'm going to describe is a way to do associative memory. Right, so I'm going to imagine that memory is made up of a bunch of pairs. The key is a string, say, over 0 and 1, and a value is, again, a string over 0 and 1. And what I would like to be able to do is write a subroutine that starts with the key written at the beginning of some tape and finishes with the corresponding value written at the beginning of the same tape. Okay? Now, in actuality, this may not be the beginning of the tape. This may be somewhere else on the tape, but surrounded by delimiters, which I can push around if I run off to the edge. But effectively, I can think of these as, this is an independent tape that I'm going to be using as an address tape, and then I want the result to be written, the corresponding result to be written separately onto some data tape, which I can then use to do other transitions. And I'm not going to place any a priori restrictions on how long the keys can be or how long the values can be. But I am going to require that for any key there is at most one value. Right? So how am I going to implement this? Well, basically what I'm going to do is I'm going to have a tape, which I call RAM. And that tape is going to be, as usual, divided up into cells. And the tape alphabet is going to be 0, 1, open bracket, close bracket, comma. Right? So if I want to store a pair, I will literally write down open bracket and then the bit string corresponding to the key, and then a comma, and then the bit string corresponding to the value, and then a close bracket. And I'll just do this over and over and over. Comma, value, close bracket, key, right? Not necessarily in any particular order. It might be helpful if the keys were in sorted order or lexicographic order, but it isn't really important. Okay? So now I have here my address tape, and I want to find the corresponding position in RAM. And so what I will do is I'll scan until I see a left bracket, and then I'll try to match symbols. And if I get all the way to the comma and there's a blank on the address tape, then I know I've found the right key. And then I start moving the head on the RAM tape across the value, writing it onto the value tape. Right? So I'll try to match these up, and if they match, I'll write onto value. If at some point I get a mismatch, then I'll reset the pointer, the head on the address tape, and scan forward to the next left bracket and do that again. And if I get a match, great. If I don't, then I reset, scan for the next left bracket. If in the RAM I ever see a blank, that means I've read the entire contents of memory and I never saw the key, and so I need to return whatever value bus error is. Right? There ain't no, that's a nil pointer. It didn't go anywhere. But that's basically it. Right? I just have a separate tape that just literally just stores memory. And I literally just scan through from left to right until I find a matching key, and then I read off the corresponding value. Similarly, if I want to change the value associated with the key, again, I scan until I get to the comma after the matching key. I erase the value that's here by overwriting it with the value on the value tape. But if I need to make room, well, I can shift the rest of the tape over to the right to make enough room if I need to write in more bits. And if I discover that there's too much room here, I only needed to write 1 bit, but I had space for 3, I can shift the rest of the tape back to the left. Again, all this shifting to the right and shifting to the left, again, happens in these independent subroutines, which for the design purposes, I can just imagine to be atomic operations. Yes?
So I guess the shifting's no cost, but...
Well, cost, but no power.
Okay.
Yeah.
Looking up the key will essentially take a little bit of time.
Well, sure. If I'm looking up an n-bit key in an m-bit memory, I might have to read through the entire contents of memory trying to match the key until eventually I find it as the last key.
But hashes work.
You're thinking about efficiency. Remember, my goal here is not to show that you can do it in a certain amount of time. My goal here is just to show that you can do it at all. Okay? Now, it turns out, if you're very, very careful, if you have a RAM algorithm that runs in time t of n, where n is the input size, by putting all of these pieces together in exactly the right way, you can simulate it on a one-tape, one-head, one-track Turing machine in time roughly t of n cubed. Right? Every time you shift, the amount that you have of work that you have to do to shift depends on the amount of data that's on the tape. But you can write at most 1 symbol onto the tape in a single step of a normal algorithm. So the total amount of stuff on the tape at any given time is at most t of n. And so just you have to do the accounting very carefully to get this to work out. But if you do it, the blow up that you get going from a standard machine where you can access any address in constant time to a Turing machine with all of the extensions turned off is only a polynomial change. Okay? All right. So I have left myself 2 minutes to describe how a universal Turing machine works. I take whatever Turing machine I want and I encode it as a bit string. So arbitrary Turing machines can have arbitrary tape alphabets, arbitrary sets of states, arbitrary input alphabets. I'm going to try to simulate it using a Turing machine with input alphabet 0, 1. So I need to encode the Turing machine as a bit string, which might be something like 0, 1 to the number of tape symbols, 0, 1 to the number of input symbols, 0, 1 to the number of states, 0, and then some encoding by brute force of all possible transitions. So I write down, if I'm in state 1 and I read symbol 3, I should move to state 5 and write down symbol 6 and move to the left. Each of those bits of that quintuple will be written down as a pattern of bits. And then I'll encode the tape for this Turing machine as a bit string. So I might have a 0 and then a field that represents the contents of the tape with a 1 in exactly the right position to indicate which symbol is at that position on the tape. So if I'm simulating a machine that has a tape alphabet of size 6, I might use 6 cells in a row to represent that one cell with a 1 in exactly the right position. And now if I want to make a transition, essentially I say, well, the simulating machine has its head here. I scan to the right until I see the state, which state I'm in, or sorry, which symbol is on the tape. And then I scan on the other tape that's storing this bit string until I find exactly that symbol and exactly my state, and that gives me the instructions for writing new states down, writing new symbols down, changing my state, moving to the left or moving to the right. There's a lot of bookkeeping involved, but essentially at this point, you can work out the rest of the details. It's good because you have minus 3 seconds. I'll say more about this on Tuesday. Meanwhile, see you tomorrow and Wednesday. Please do not forget, if you need to take a conflict exam, please see the form that's linked from the course webpage. Thanks.